Okay, hello class. Today what we're going to be doing is going over lesson 1, an introduction to waves. This is part of physics unit 2. All right. What I would like you to do is make sure that you remember to put your name, your period, and the due date on top. Okay. So don't forget about that. First thing that we're going to cover is lesson 1, introduction to waves. Okay. Now the objective is basically to develop an understanding of the various types of waves, how they function, their properties, and interactions. Okay, so section 1 deals with the nature of waves. This is found in chapter 20, and you can find this on pages 574 to 579. Okay, now waves, if we want to give a definition, these are any disturbance that transmits energy through matter or empty space. So any disturbance that transmits energy through matter or empty space. Okay, so these are more than just your common water waves. Okay, now mediums are what a wave travels through. Okay, this is the substance through which a wave can travel. So a medium is a substance through which a wave can travel. And this can include water, air, solid liquids, or gases. Okay? So waves that require a medium in order to transfer energy are known as mechanical waves. Mechanical waves. Okay, so those are mechanical waves. Examples of these include ocean waves or seismic waves. Okay, so the medium in these cases are water and solid earth. Okay, waves that do not require a medium in order to transfer energy are electromagnetic waves. So electromagnetic waves. Okay, these do not require a medium. Examples of these include different types of waves throughout the light spectrum, such as X-rays, gamma rays, radio waves. Okay, there's many good examples. Though these do not require a medium, but they can still go through glass, air, or water. Okay, so now we're going to cover the different types of waves. Okay, this includes transverse waves, longitudinal, and combination waves. So the first thing that I'm going to do is define a transverse wave. Okay, a transverse wave is a wave in which the particles of the medium move perpendicularly to the direction the wave is traveling. So basically at right angles to which the wave is traveling. Okay, so now what I'd like to do is I'd like to draw a transverse wave. Okay, now transverse wave is basically like a rope. Okay, it's if your friend is at one end and you're at the other, it's like you're shaking the rope up and down. Okay, now these different waves have things that we need to point out. For instance, the crest is the highest point on the wave. Okay, and the troughs are the lower points on the wave. Okay, so These would be the high spot, and this would be the low spots. Okay. Now, like I'd said before, this is basically like if you were holding a rope and shaking it up and down. Okay. Now, like we said, the wave is moving in this direction. Okay. So this is the wave direction. But the particles are moving at right angles to which the direction is traveling. Okay. They're moving up and down. Okay. So that is a transverse wave. Now, a longitudinal wave is a little bit different. This is a wave in which the particles of the medium vibrate parallel to direction. So direction, I'm going to extend that direction of wave motion. So basically, in the same direction. Okay, these are longitudinal waves. A good example of a longitudinal wave is a sound wave. Okay, for instance, sound waves produced by vibrating drums form compressions and rarefactions. Okay, and I'm going to draw a longitudinal wave. It's basically like a slinky. So the rarefactions are the area where they're spread apart, and the compressions are the areas where they're very close together. Okay, the particles are close together. And now I'll draw another rarefaction over here. Okay, so these are the compressions. This is the area of compression, and this is the area of rarefaction. Okay, so rarefactions are the areas where the particles spread. Okay, and this is the area where they crowd together, the compressions. So crowd. Okay. Now, there's one last wave that we need to discuss, and that is a combination wave. Okay? Combination waves are waves where two waves interact with one another. So a wave where two waves interact with one another. Okay? Now, ocean waves, for example, they have properties of both transverse and longitudinal waves. Okay? Also, electromagnetic waves, these are basically two transverse waves moving horizontal to the direction of the wave and vertical to the direction of the wave. So there's two transverse waves. So these are combination waves. Now what I'd like to do is move on to section 2. Okay? Now section 2 talks about the properties of waves. Okay? This is chapter 20.2. And I'll just put this in here. It's pages 580 to 583. So pages 580 to 583. Okay? So what we're going to discuss first is amplitude. Okay? Amplitude is the maximum distance that the particles of a wave's medium vibrate from their rest position. So this is the maximum distance, that the particles of a wave's medium vibrate from their rest position. Rest position. okay? So that is amplitude. Now, what we need to do is draw a wave so we can discuss where amplitude is found, okay? So here's our baseline, and now the wave, similar, in this case, we're talking about a transverse wave. If you take a look, okay? Now, I want to point out that this is the amplitude of the wave, okay? And so if we're cutting the wave down the middle, basically, and this is also the amplitude, okay? And like I said, this is the max distance that the particles of a wave's medium vibrate from their rest position. So the rest position is that central base line, okay? As the amplitude goes up, the energy will increase, okay? So this is point from center to the peak or the trough of the crest, okay? So now we're going to talk about wavelength, okay? Wavelength is the next property. Now wavelength is the distance from any point, okay? So the distance from any point on a wave to an identical point on the next wave. Okay, so this is wavelength. All right, so now as the wavelength decreases, the energy is going to increase. Now, wavelength is measured from crest to crest or trough to trough. And I'm going to try to point that out. In this case, we will go from trough to trough. We discussed what this was. So in this case, this would be the wavelength. Okay, and I'm just going to mark this down. This was the amplitude before. Okay, so that is the wavelength. It's actually from trough to trough, or crest to crest. So now what I need to do is discuss what frequency is. Okay, frequency is the number of waves produced in a given time. So the number of waves produced in a given time. Okay. Now, frequency is measured in hertz or waves per second. Okay. So measured in hertz or waves per second. And this is capital H, lowercase z, that's hertz. And okay, so waves per second. Now, I'm going to point out just an example of frequency, okay? And we'll do it here. So frequency, an example of this would be 10 waves in 10 seconds, okay? So 10 waves in 10 seconds, okay? 10 waves in 10 seconds. So basically, this is going to equal 1 wave per second. Okay, so that would be frequency, and then that could be measured in hertz. So if a wave type has equal amplitudes and frequency, and the frequency of one is higher, okay, that means it's going to be more energy. So frequency can increase energy as well, okay? You've probably heard of waves that have a higher frequency. So the last one is wave speed. Now, wave speed is the speed at which a wave travels. This is the speed at which a wave travels. Okay, so this is wave speed. Now the equation for wave speed is wave speed equals wavelength times frequency. Wave speed is equal to wavelength times frequency. And in the textbook, you can see that there's different letters and symbols. In this case, we'll write this as V is equal to lambda. That's going to be the wavelength times F, which is the frequency in hertz, okay? So an example of this, we'll write this down. This is the wavelength, is going to equal 4 meters, because wavelength is in meters, and the frequency is going to equal 360 hertz. Okay, so this is an example. Now, if we multiply 4.0 meters times 360 hertz, or waves per second, we are going to get a velocity of 1,440 meters per second, okay? And now what I'd like you to do is start and watch the second podcast for the rest of L1. Now this is on the back side of your foundation worksheet where the other information for L2 is located. So you're going to have to flip this over at this time. Okay? So now we're moving into section 3. Now section 3 deals with wave interactions. This is found on chapter 20.3. Okay, so section 3. I'll point this out. This is pages 584 to 589. 589. Okay, so this is where wave interactions are found. The first thing that we need to do is discuss reflections. I'm sure many of you have heard of reflections before, or you can look at yourself in the mirror and see your reflection. Okay, this is based on light though. So the reflection is the bouncing of a wave of light, not only light, but light, sound, or heat when the wave hits a surface that it does not go through. A wave hits a surface that it does not go through. Does not go through. It is reflected. Okay. Now, when waves bounce back after hitting a barrier, and a good example of this would be light waves that are reflected off the moon. Okay, that allows us to see the moon. Okay, so the moon isn't producing light on its own. An example is a reflected sound wave is called an echo, and I think most of you know this. You've probably produced echoes before for the fun of it. Maybe you're on a camping trip and you're yelling across the lake and you could hear your echo. Okay, that can happen. Now, refraction is the bending of a wave as the wave passes between two substances in which the speed of the wave differs. As the wave passes between two substances in which the speed of the wave differs. Speed of the wave differs. Okay, it differs. Okay, an example of this is when a light passes through a water droplet. Okay, through a water droplet, it is dispersed, allowing us to see different colors. Okay, so it is dispersed. Now, just to talk about that a little bit, it basically separates the colors, okay? And in this case, it is based upon the wavelength, okay? So it's dispersed, allowing us to see different colors. Now, a light wave will change its angle as it passes through something like water as well, and it'll have a certain refractive index, okay? So light will be bended if you shine something like a flashlight down into water. It will bend. Okay, so diffraction is the next one. This is a change in the direction of a wave when the wave finds an obstacle or an edge obstacle or an edge or slash opening. Okay, so this is diffraction. Okay, now for instance, sound waves, these have longer wavelengths, so they can be diffracted more easily than light waves, okay, more easily than light waves. And now diffraction, this is, once again, it's the change in the direction of a wave when the wave finds an obstacle or an edge slash opening. Now, sound waves can reach or around or curve or bend around buildings and can be heard. For instance, if you're walking down a city street and there's music coming from behind a building, okay, you can still hear it because of diffraction. Okay, so it happens more easily with waves that are longer, that have longer wavelengths. Okay, the last one is interference. Okay, now interference is the combination of two or more waves that results in a single wave. Okay, so this is interference. Now, there are two types of interference, okay? Now, these two types include constructive interference and destructive interference. So, constructive interference, we'll just write I for that, so INT, interference, and destructive interference. And I'm sure you've heard of interference before, I guess with regards to sound waves or maybe radio waves, okay? Now, in this case, interference is when the crest of one wave overlaps with the trough of another, and it has a smaller amplitude, the energy of the wave will then decrease, okay? So constructive interference is basically a little bit different than what I just described, which is destructive, okay? So what I just described was destructive, whereas constructive is when, in this case, I'll underline this, so constructive is when the crests overlap, okay, overlap other crests, and they have higher crests with deeper troughs. This will form more energy. So you'll see that they're kind of in sync in constructive interference. In destructive, it was what I just described before. This is when the crest of one wave overlaps with the trough of another, and this forms smaller amplitudes. The energy of the wave decreases. You can see this in water waves as well, and you'll see this throughout the unit more. And that is all that we have for Lesson 1 of Physics Unit 2 on waves.